Dr. Fox is an associate professor in biosystems and agricultural engineering at Oklahoma State University. After growing up on a farm in Texas, he received his master's and master's at Texas A&M, his PhD at Colorado State. He has conducted extensive research on the role of groundwater, both independently and in concert with other forces, in leading to stream bank erosion and failure. I think it's interesting in his short tenure of only about 8 years since receiving his PhD, he's authored about 50 scientific publications and garnered almost $5 million in research support. I think that says something about the quality of this individual. And Dr. Fox, we're looking forward to hearing the topic, Understanding Stream Bank Erosion and Stream Sediment Loading.
Excellent. Can you guys hear me in the back? You guys okay back there? Greetings from the state of Oklahoma. When I left Tulsa, Oklahoma yesterday morning at 7 a.m., it was 85 degrees. When I got to the Twin Cities and arrived about 9 o'clock yesterday morning, it was a cool 55 degrees. I would like to take some credit for the nice weather outside. I think I brought it with me. Okay. I don't know if that's part of climate change or not. I think the comments Dr. Seeley made are right on target. We're seeing the same things from our climate scientists in Oklahoma. There's a very nice climate survey and climate research facility at another university in Oklahoma. We won't name that university today. But they're basically saying the same thing, and it was very interesting to hear those comments. They're basically saying that, we're going to experience periods where we're going to go through droughts, and we're going to go through periods of very intense rainfall that happens in short amounts of time in the same year, and we have to prepare for that. Okay. I showed my presentation to my wife and my 5-year-old daughter before I left. My wife said, "You need more jokes." My daughter said, "You need more pictures of animals." So I'm going to start with both. I don't have a picture of an animal, but I'm going to start with a joke. And I borrowed this joke from a training session that I went to recently. But there was a lot of engineering students at this one university, and engineering is kind of a hard subject for a lot of students to do. If you do want a very good degree program, if you guys have kids, I would suggest go into some area of water, okay, because it's going to be a big issue. But these engineering students for 10 years would take this very easy technical elective on bird watching. And so there were engineering students year after year after year that would go to this class and they would do a bird watching class. Okay? And the class was very, very easy. Easy A, no problem. So finally one year a new professor came into the university and he was assigned to teach the bird watching class. Okay? And he ended up deciding that he was tired of all these engineering students coming over to take his class. So he was going to make the class a little bit harder. So he had about the same amount of enrollment the first day of class, and then the students started figuring out that this was going to get harder and harder as they went. So what ended up happening is a lot more engineering students started dropping and dropping and dropping, and by the end of the semester he had about 50% of the class left over. And usually the end of the semester, the final was like a pizza party, and that's all you did. Well, this professor walked into the room pulling a cart, and he had shoe boxes. And there were birds' feet sticking up out of the shoe boxes. Okay? And the final exam, he had a dozen of these, and he said the final exam was, based on the bird's feet, you have to tell me what type of bird it is, what the plumage is for a male and female. You have to tell me the migratory patterns of all of these birds. Well, there was this engineering student in the back of the room, and she said, "This is ridiculous." Basically took her books, threw the books on the floor. Professor walks to the back of the room, says, "Young lady, what's your name?" And she paused for a minute. She took her shoe off, stuck her foot in the air, and said, "You tell me." So what's that got to do with stream banks? Well, what's it got to do with my presentation? I hope by the end, I don't have 50% of you guys left, and I do not need to see your feet today, okay? But I will show you some work that we've done where you can get your feet muddy, and you can lose some shoes and get some feet really, really muddy in this work. I am not here as an Okie or as a new Okie, relatively new Okie. I'm not here to tell you about Minnesota, okay? That's not my job. But what I'm going to do is I'm going to show you some of the basic fundamentals that might help you when you're looking at your stream systems and you're looking at your banks. And what I'm going to show you, and what Dr. Gupta is going to show you later, is that some of these same things that you guys are experiencing, we're seeing across the country. And so there's a great opportunity here for us to kind of share ideas, come together and work together on these issues. What I want to start off by saying is that I want to start with a kind of a bigger picture view of streams. Streams are dynamic, okay? The pictures that you saw today, the aerial photo and the stream moving, okay? Streams want to move, all right? They don't want to stay in place. They do want to get to an equilibrium state, but that equilibrium state is one where it is dynamic, okay? And streams have a different equilibrium or a different dynamic state associated with them. We can talk about that in terms of a plan form, but we can also talk about it in terms of stream bed elevation, okay? So stream bed elevation can change. It can move up or down. And we can talk about it in terms of its cross-section, okay? Streams are not intended to be channels that look like open pipes and the water just to run through that open pipe. They are actually supposed to spill over onto their floodplain, because in a lot of cases we have floodplains that have vegetation on the surface, right? And that vegetation interacts with that water and it interacts with that sediment, okay? So we need to keep these things in mind when we start talking about stream systems. Now there's a lot of different ways streams can get off of this equilibrium. And there's a lot of different ways in which you can start getting issues with streams, and streams can start migrating faster than maybe what they naturally should migrate, however we might define natural, okay? Some of those disturbances include in-channel disturbances, okay? Anybody had any streams straightened or dredged, okay? Those issues, we have those issues in Mississippi, we have those in Oklahoma, okay? That can throw a stream off of its equilibrium, okay? Ag activities, okay, can have an influence on what happens with streams, but either positive or negative. Urban areas, somebody mentioned urban areas in the back, okay? When you have an urban area and you put increased impervious surfaces on the landscape, that water's got to go somewhere. It's not going into the ground, it's going to run off, it's going into the sewers, and then eventually from the sewers and the drainage ditches, it's going right into the stream. And it's a very high carrying capacity for water and sediment. These are some of the streams that we've studied or investigated or played a role in several different parts of the country. Goodwin Creek, Mississippi is probably one of the most famous studied stream banks that I know of. There's more data probably at Goodwin Creek than any other stream bank site that I've seen. This is Sugar Creek in Oklahoma. It's a sugar sand. And if you can only imagine how fast the soils erode there, if you're talking about a sugar sand. And then we've looked at pictures from Iran, pictures from Iraq, pictures from all over the place where these processes are occurring. And when streams get out of equilibrium, what ends up happening is you see these very steep banks. Okay? Because they can get out of equilibrium in several different ways. One of the ways they can get out of equilibrium is the stream bed can actually cut further and further and further down. Now from what I understand from your Minnesota rivers is you kind of had a glacier that helped to do that a little bit, right? But that's a process where the stream kind of got kicked out of equilibrium. Okay? But when they get steep, then these banks become very unstable. And what I'm going to try to do is to just give you some fundamental background about how we can quantify some of that stability. Now there is something that has been developed by researchers across the country that talks about the migration and the patterns and the processes that streams undergo. Okay? And that's called what is referred to as the channel evolution model. And the channel evolution model consists of basically 6 different stages. It's got a stage 1, which is a pre-modified natural channel. Okay? Bed's probably pretty stable. The bed could be, stream bed could actually be coming up. We could be having aggradation on the bed surface, but that's stage 1. Typically, if there's some kind of a disturbance in your system, you go into a stage 2 channel. And a stage 2 channel, basically your stream bed starts to drop. We get degradation. So basically, we get some erosion of the banks, but the bed is starting to drop a little bit lower. And you're starting to see the banks start to steepen up. Stage 3, the bed gets even further. The bank slopes get higher. These become more unstable, eventually leading to a stage 4 where you get degradation and widening. Okay, so the bed's not only going down, now the banks are starting to collapse in. And what researchers hypothesize is that eventually, after stage 4, you get to a stage 5 and a stage 6 process where the streams almost naturally heal themselves. Okay, the bed's dropped far enough below, it's widened out, you get aggradation of that material onto that stream bed, and what ends up happening is you have a stream now with actually almost like a dual floodplain system. Okay? And it's almost reconnected back to its own new formed floodplain. A lot of times what we see is, and I've heard a lot of talk about this in the last couple of days that I've visited here, is you see nick points that start developing. Okay? And those nick points typically migrate upstream. And so what we typically find is that these stage 5 and stage 6 streams are usually downstream where we've got an aggraded bed. Okay? Could be coming into a reservoir. And then typically where we're seeing a lot of the failures and a lot of the stream bank stability issues are right below that nick point. And some of our more stable stream sections are actually upstream of that nick point. All right, so kind of the take-home message then from that is that stream bank erosion can be significant. Drew's results basically demonstrated that extremely, extremely well this morning. And it's not only here in Minnesota. It happens everywhere. Okay? Andrew Simon, who was at the National Sedimentation Lab, did a lot of work in some southern watersheds, especially in Mississippi. They found as much as 85% of the sediment load in some of those watersheds was coming from stream banks. Okay? There's been other studies in agricultural watersheds where it's 54 to 80%. Okay? And it's relatively new because a lot of the stream bank work actually started about the 1970s, 1980s, and people started looking at these processes. And so this is not a situation that just occurs in Minnesota. It occurs in other places. Now, what I want to tell you about today specifically is a lot about the mechanisms that actually cause these banks to collapse. Okay? Because I think if you understand the mechanisms, then we can start to understand some of the possible solutions, if there is a solution. And in my opinion, as an engineer, I think I have to do this as an engineer. As an engineer, I think I can have a solution to anything. It just depends on how much money you want to pay me. Okay? So if you want to write a $2 million check today, I think I could probably do something. Okay? It might not solve it forever, but I bet I could slow it down. Some of those mechanisms, and this gets a little bit, scientific, and I think when Warren invited me to come, he said, well, we want to know, the state of the science. Those mechanisms include fluvial mechanisms, and what I'm talking about there is just the stream flow. Okay? When the stream flow gets up, stream flow is going to erode particles. Right? It's going to erode sediment. It's going to erode it on the bed. It's going to erode it on the banks. One of the other mechanisms where you can get sediment loading into streams from stream banks is something called, it's a fancy term, it's called geotechnical failures. It's basically just a collapse. Okay? But these things don't occur independent. They're combined. They have an interplay with each other. The other thing that can cause a bank to collapse, and one of the really, really interesting problems that Dr. Gupta is working on here, my research team is working on in Oklahoma and Mississippi, is that groundwater can actually be a very important player in causing banks to erode. Okay? And we'll talk about that more as we go. I'm going to show you a laboratory experiment that we did. And this laboratory experiment, you're going to see it twice today. But what I wanted to do is I wanted to show you this up front because I wanted you to get your mind wrapped around, a bank collapsing and what it looks like and what are some of the processes. And what this bank is this bank has a couple of different layers in it. There's a more non-cohesive layer here. It's like a sand layer here. And then there's a topsoil material right here. Okay? And what we're doing is we're looking, the stream is basically here. Okay? And we're looking if we could somehow, if we were Superman, right? We looked inside the soil. This is what we're looking at. Okay? So what you can see though is what typically happens in a lot of the banks, and I'm not saying that this happens here in Minnesota, but what happens in a lot of the banks is we'll get some kind of an undercutting formation that will occur at the toe of that bank. And that undercutting formation can be by stream flow, fluvial, or it could be by groundwater. Okay? It can be by a number of different mechanisms. And then what eventually happens is when you get an undercut bank, you get something that is called a tension crack that actually forms in that bank. And that tension crack, usually in a 2D it's a line, but in a 3D it's usually circular. Okay? And that tension crack usually reduces the stability of that bank, and then it can basically cause that bank then to collapse in. Okay? So we're gonna kind of keep that in mind as we go throughout the presentation. Okay, so how do we handle fluvial erosion? From a scientific perspective or from an applied perspective, if we're going to go out and analyze a bank, how can we determine the susceptibility of that bank to fluvial erosion? And I promise you, I had a hard time, but I promise you this is the only equation I have in the presentation. Okay? And this one is not that difficult of an equation. It's simply a linear. This little a is just 1. I could have probably even just left that out. Most people assume that value to be 1. This is an equation that's called an excess, to to sound really good for the camera. It's called an excess shear stress equation. Okay? For you guys, all you need to think about is it's basically just a force equation. And as an engineer, we like to study forces. So this little term right here, which is a Greek letter tau, okay, that little term is basically how much force do I have to put on the sediment before it starts to move. Okay? And this little tau parameter here is how much force does the water have. Okay? So all this equation is saying is how much force do I have compared to how much force do I need to make it move. And if I don't have enough force, then it won't move. If I do have a lot of force, then it will move. And the rate at which it moves is this little k value. All right? And that's basically how we model a lot of erosion due to fluvial forces. Now those parameters, there's a number of different ways to estimate those parameters. Sometimes it's easy, sometimes it's not so easy. But there's a very good technique that was developed by Greg Hansen at the USDA ARS Hydraulics Lab in Stillwater, Oklahoma. And that's something called a jet test, okay? A jet erosion test. And this jet erosion test is something that we can use. We can actually go out on a stream bank. What we do is we put this thing up against a stream bank and we force a jet of water to basically impinge on the stream bank. And it causes basically a scour hole. And based on the size of the scour hole and how fast the scour hole forms and what the equilibrium depth of the scour hole, we can actually estimate those two parameters for your stream bank. So we can come back in and we can say, okay, well, this stream bank has a tau c of this and a kd value of this. And then what we can do is we can look at the force of different stream flow events and we can know how much fluvial erosion actually occurred due to that event. There's even something, he's even developed something, this is the larger jet, he's even developed something called a mini jet, which even makes it even easier to use out in the lab. So that's one part, right? That's the fluvial part. But the question is I told you there were more mechanisms than just fluvial. There's also the failure, right? I think that's Dr. Gupta. We need a way to figure out whether the banks are going to collapse and how stable they are. And what I can tell you is based on the banks I saw yesterday, you have a lot of unstable banks, okay, in Minnesota. I grew up in Texas. They said everything's bigger in Texas. Well, based on what I saw yesterday, there's some stuff bigger in Minnesota. Okay? Slopes fail a number of different ways. Okay? And when we have a bank that fails, it can fail a lot of different ways. One of the ways we can have a bank fail, and this is for any slope, it doesn't have to be a stream bank. It could be a landslide in California. All of the analysis is basically the same, which makes it really neat. Okay? But you can have a rotational slide where this material just gets too heavy and it just slides down. Okay? You can have, even if you have an ocean, you can have a cantilever failure. Okay? Cantilever failure is like I showed you in that movie, right? Where the material gets undercut and then it collapses. That's a cantilever failure. You can also have translational slides and flows, okay, that can occur. So what factors do we have to measure to figure out whether a bank is stable or not? And these are important factors that you need to consider when you're looking at maybe your system. One of those is the slope. Okay, the slope is a direct correlation to stability. The steeper the slope, the more unstable you've got. Okay, so slope is a very important factor. Another very important factor is the soil type and the strength of the soils. Not all soils are created equally. Okay, I learned that in soil science. Okay, not all soils are created equally. And not all soils have the same strength. Okay, and when we talk about strength of the soils, what we're really talking about is almost the intermolecular bonds, okay, and the frictional resistance between different soil particles. Okay, there's a couple of parameters there we call the cohesion and the internal angle of friction. And those parameters are very important for us for quantifying a bank. I can modify those parameters. Okay? I can change those parameters. I can take two different soils with the same slope and I can get drastically different results because of this, basically the strength is different. The other thing you have to keep in mind here, and I think you're going to see this, and this is where the implication comes in for you and your management and land use, is the action of water is very important from a stability perspective. Okay? We already talked about fluvial. That's one way water can act on a bank, right? The stream flow can act on that bank. Okay? You can also have something called seepage, and I'm going to show you a lot about that here in just a minute. Okay? Seepage has an impact on your bank material. Okay? There's also something called pore water pressure. All right? When I grew up in Texas, I grew up on a beef cattle farm. And I don't know how, but fences got torn down all the time. Okay? And so we didn't have the nice little implement you put on the back of the trailer, back of the tractor to drill the hole, put the fence in. We used a post hole digger, okay? And I can tell you, right, what would happen if I went out to the field and I was trying to put in a fence post and the soil was really dry? Oh, it's horrible, right? That's when I said, we should let my brother do it, right? So we should let him dig that hole, okay? And I figured out this pretty early that, hey, if I wait and let it wet up a little bit, that soil is going to be easier to dig out. And it's the same thing with a bank, okay? So remember, I was talking to you about these grains and them being in contact and then having a bond and it having frictional resistance. Well, if you put a little water in there, it's almost like having a little viscosity between that. Helps those grains move a little bit more. So water is actually one of the ways in which we can get, basically, we can actually reduce the strength of the soil. Okay? So water helps us to reduce the strength of the, or maybe it doesn't help, but it does reduce the strength of the soil. The other thing water does is it provides a confining pressure. When the stream stage is actually the highest, one of the things it does to that bank, even though it's eroding particles, is it actually helps the bank hold up. Okay? So that's actually another force that water has. One of the other forces of probably action of water that I don't have listed up here that maybe I should have listed up here is freezing and thawing, right? One of the most interesting things I saw is on the Goodwin Creek stream bank in Mississippi is when that soil, when we had one freeze event that year, okay? And when I went out, yeah, lucky, right? I'm coming up here for the summers. I'll be back down there for the winters, so, okay? So with that one freeze event, it was amazing, but you could go out and you could basically peel sediment off of the bank, about 2-3 inches thick, okay? So freeze and thaw are very important for stability. It's a way that we can remove material. Vegetation, we talked about a little bit earlier today. Vegetation is important for stability, but there is actually a fairly large debate right now, the fact that vegetation has both positive and negative influences on the stability of a bank, okay? It's both positive and negative. And it depends on what kind of perspective you look at. We're going to talk about that more in the next slide. The way that we calculate stability is we calculate this using something called a factor of safety. Okay? And a factor of safety is very simple. It's just the resistive forces, what's holding the bank up, divided by the driving forces, what's causing the bank to collapse. So when your factor of safety is equal to, or when your factor of safety is less than 1, what happens? It's gone, okay? So if you're sitting up there in your lawn chair and you pull up your computer, and I'll show you a computer program you can use in a minute, and you calculate factor of safety and it says less than 1, back up, okay? If the factor of safety is greater than 1, you're stable, okay? And so we have a tool that we can use to do that. Now let's talk a little bit more about vegetation. Why did I say positive and negative influences of vegetation? And this is primarily going to talk, well, we can talk about vegetation on the top of the bank. We can also talk about vegetation on the face of the bank. It has both mechanical aspects and hydrological aspects. The mechanical aspects are that the roots increase the strength of the soil. Okay? Roots increase the strength of the soil. The best analogy I've heard to describe this is that roots are like rebar in concrete. If you've ever laid concrete, okay? And you've put the rebar in, you know how strong that material can get. Roots are like rebar. To stabilize a bank, you need a root system that's as deep of a root as you can get, and that's got a very nice root system associated with it. Okay? From a mechanical aspect, the negative part of the mechanical is actually something we call the surcharge, and that's just a fancy way to say it adds extra weight to the bank. Okay? And I can promise you, we had discussions with the U.S. Army Corps of Engineers in Sacramento. Sacramento's got levees. They've got large trees growing on their levees. And they were debating, as recent as a year ago or so, they were debating whether there was too much surcharge by those trees on those levees. Okay? Now, vegetation also, I don't know how I did that. Vegetation also has a hydrologic influence. Okay? So it has... One of the things that vegetation does is it intercepts the water before it gets onto the bank, right? So you get interception. And that material is stored on the leaves and then generally it evaporates right back out. And then you don't have to worry about that water being in your bank. The other thing vegetation does is it actually takes water out of the soil. And that's a good thing, okay? Because that can help with the stability. There's some work that has suggested that vegetation actually can increase your infiltration capacity, though. Okay, that there can be macropores and openings next to roots, and it can actually cause increased infiltration capacities through there. So let me show you how you calculate the stability of a slope. Okay, so we've got all these forces, all these different things that come into play. So all you got to do is you got to figure out where the failure plane is, okay, which is not a trivial task. Then you got to put all the forces in. You got to decompose the forces in their different directions. Okay, and then you got to figure out the pore water pressure. You got to decompose that into its different directions. And then you got to figure out the resistive force, which is based on the cohesion of the internal angle of friction. That's all you got to do. Okay, it's as simple as identifying what bird based on its feet. Okay, so if you can do that, you can do this. But yeah, no, this isn't easy. Okay, and so what we use is we use computational tools that help us to do this. Okay, and I'm going to show you. And there's several different computational tools that are out there, but I'm going to show you one that's been really designed specifically for banks. And that's called the Bank Stability and Toe Erosion Model. And that was developed by Andrew Simon and colleagues at the National Sedimentation Lab. It simulates a 2D stream bank. It estimates the fluvial erosion, estimates the factor of safety, and then it comes back and it updates the bank profile. So you can actually simulate a bank. You could actually go out and simulate your bank on your property. Okay, and you could actually put in the parameters for that, and you could simulate the process over time. Okay, this is a bank. This is BSTEM. This is one of the menus in BSTEM. Okay, all I want you to look at. Don't worry about all this other stuff. Okay, just watch this bank here, and I'm going to show you what BSTEM will do. Okay, so BSTEM, again, what it's going to do is it's going to run a series of simulations. We're on about January 2008 here. This is just a hypothetical bank. This is not your bank. Okay. What you can see is it will erode the toe a little bit. There's a stream flow event happening. It erodes the toe. This jumped just because of the input in the figure. Okay? You see a little bit more erosion, a little bit more erosion. There's the stream stage actually up, so we've got some erosion that's happening. Continues to cut, continues to erode, continues to erode. We got lots of erosion. We had a big flow event. Okay? Stream stage is all the way up here now. We've even got some erosion of this top material. And what you can see is that material has gotten steeper. Water level went back down, and then we've got a bank collapse. Okay? And you can do that. You can run that for a bank, and we can understand the properties of the bank. What this really helps us to do is not necessarily understand how the bank operates over time, but it helps us to look at solutions to solving maybe an issue if we want to try to stabilize this bank. This is a bank, and I'm going to show you a couple of different things, and this is where the quiz is going to come from. Okay? So pay attention to this. Okay? Here's the factor of safety we were talking about, right? Factor of safety less than 1 means get out of your lawn chair, scoot back. Okay? Factor of safety greater than 1 means you're fine. Okay? Have another drink. Whatever your choice is. Okay? So here's the bank, same bank we were dealing with. Here's the failure plane. This is actually the groundwater table. Remember how I was telling you that groundwater is important within this system? Okay, so this is the groundwater position. And we're at a 1.55. We are a stable bank to start with. Okay? Then let's go through a storm event. So we have a storm event that occurs. Okay, storm event, stream stage rises, we get a little bit of erosion here. Uh-oh, what's the erosion done to our bank? Well, it's made it steeper. Uh-oh, that's reduced stability. Okay, what else has happened? The groundwater tables come up. What happens when the groundwater table comes up? It's easier for me to dig that post hole, right? The soil ends up getting wetter. And if you're going to compare two banks, same soil material, same slope, one's wet, one's dry, the wet one's heavier. Okay, so it wants to collapse. Also, the cohesion here is less in this bank, and we've got a 1.24 factor of safety. And some people call that conditionally stable. And conditionally stable means it's stable, but we're not sure because there's uncertainty in the parameters. Okay, but in general, it's stable, as long as you measured your parameters right. Okay, this is the next step. The stream stage just went up higher. The groundwater table went up higher. Factor of safety went up. Do you know why? Water's holding it. Okay? The water's confining it and it's holding it up. Okay? So the factor of safety actually went up a little bit. Now, what ends up happening is typically when you have an event, you've got the water table high, you've got the stream stage high. Which one of those is going to drop first? Stream. Okay? Excellent. You guys are hydrologists. Okay? So yeah, stream stage is going to drop first. Okay, groundwater table is still going to be high. Factor safety's in trouble. Okay, and we've got collapse. And we've got tools available that we can do that. And it's all process-based. Okay, so it looks at the processes that occur. And what's really interesting here is to note it's not one or the other. Okay, so if you go out to your bank and you say, oh, my stream flow is killing my bank. Well, I would probably tell you, no, it's probably not that by itself. Okay, it's probably a combination of these two things. This is a hydrograph for some banks that we studied in Oklahoma. And one of the things I want to point out is the same thing you guys just noticed. This is the hydrograph. Okay, so this is water level versus time. And these red dots are where we saw a collapse. And what you see is the collapse doesn't occur when you have the highest water level, the highest flow. It occurs when that water, a lot of times it occurs when that water level drops back down. Okay, so that the whole interplay is very important. Okay, let me talk a little bit about what we've seen relative to seepage. Okay, and the banks that we toured, we had a fabulous tour yesterday. I think you should all sign up for the tour. I think that's later today, right? You should all sign up. You should go see some of these, and I think Dr. Gupta is going to show you pictures of these banks where it looks like we have seepage processes going on here in this watershed. Okay? I'm going to show you a little bit about what we've done in some different places and how some of the processes might be similar. Seepage erosion is a process which occurs basically when we have a lot of pore water pressure and we have a lot of water in our banks. Okay, so we might get precipitation that might infiltrate, and a lot of the banks we studied in Mississippi have this clay horizon. It actually comes down, hits this clay horizon, and then it's got to go laterally, right? And when it comes out laterally, it can cause erosion of that bank. Now, one of the interesting things we see in Oklahoma, and we see in some parts of Mississippi, we've seen it in other places, Kansas, some other places, we see cave-like structures on the side of our banks. And those caves are actually where the seepage is actually coming out. Okay? There's one spot where the seepage starts to come out. And what some people have suggested is that while seepage might occur over a long distance of the stream, when it starts to come out in one spot, you actually start to converge the flow to that spot. And so we actually see some of these, I have to call them undercuts because the gullies guys that do head cuts don't like that term. Okay? These are some of the bank failures that we've seen. This is Dr. Glenn Wilson, who is one of my co-PIs with the National Sedimentation Laboratory. You can see some of the undercut features there on these banks caused specifically by seepage erosion. We've actually gone out to these banks. We actually usually send graduate students because it's very treacherous. But what we will do is we'll actually try to find these seeps, and we'll actually go in and we'll put in lateral flow collection pans. And we'll collect data coming out of this seep to try to look at flow rates and sediment concentrations coming out of this, and basically for us to better understand the mechanism. Here's one of the seeps that's on the side of a bank. It's coming out of old slough material, and the material basically, once it causes a seep, it can undercut it and then cause that bank to collapse. Okay? This is the lab experiment you saw earlier, right? So you say, I've seen that already, but maybe you were asleep the first time. Okay? So this is the same thing. I didn't tell you how this was eroding, but what we're doing is we're filling this backside up with water, and water is actually flowing through this layer, and it's actually causing that to undercut just by groundwater. There's no surface water acting here. It's all just groundwater. Okay? And groundwater by itself can cause that bank to collapse. Okay? We've done some modeling work that's actually suggested, remember that factor of safety term we talked about? We did some modeling work to show that undercut actually causes the factor of safety to decrease really fast. You don't need much of an undercut to cause instability. Okay? We've even done some three-dimensional laboratory experiments. So we've gone to a three-dimensional case because we didn't want to look at just 2D. We wanted to look at 3D. And this is a sand soil. So these are very simple cases because a lot of people don't understand the mechanisms, and so we wanted to understand those mechanisms. This is a sand soil. It's packed pretty light. Okay? And what I'm going to show you with this soil is you got a little bit of water come out, but what you'll notice about this bank is, bam, it's gone. Right? Where's the undercut? Well, the bank wasn't strong enough to hold up to the seepage force. When you have seepage moving through a bank, water molecules are traveling through the soil. They're basically pushing, okay? And those water molecules basically just push that bank out. If I go to the same soil, but I go to a little bit higher bulk density, I increase the strength of the soil, then I see an undercut, and then it collapses, okay? So depending on what kind of soil you have, seepage may never show itself, or it may never show itself. You may never see a cave, okay? You may just see a pop out, and you may never know it's there, okay? But it is, okay? And it's most likely it is. We've also done some additional seepage erosion experiments in Mississippi. We just got done with this, and this is kind of hot off the press type stuff. We just submitted a conference paper on this. One of the things we like to do is to try to make banks collapse, okay, which is kind of not a good thing, but we do like to do that. Okay? So one of the things we did is we identified a location with seeps. Here's the bank. Here's some of the seeps that we ended up forming. We actually put a trench in. Okay? I don't know why the landowner let us do this, but he did. Okay? And so we actually filled this trench up with water, and then we had basically instruments. There's our trench that we're putting in. It was about 8 feet deep. Okay? And we had instruments, observation wells, and tensiometers to measure how the water's flowing and how it flows and what's happening. And we measured what was going on within the system basically over time. And what we ended up having is in identified seeps, we had a lateral flow collection pan, and it was routed basically to a PVC pipe that we could route it down and then collect measurements over time. Okay? And we found some really interesting information from this, okay, about mechanisms and about seepage processes. This is some data that we collected from one of our seeps. This is time versus the flow rate, and then you could also do time versus the erosion rate. And just note the magnitude. These are 0.5s, okay, these are thousands. We did the experiment 2 different ways. One of the ways we did it is we'd let the seepage come out, and the material would deposit. Okay, so we'd have a collapse, and then that material would be deposited there, and the water would still have to flow through that material. Okay? And what you notice in this graph is that we have a really high erosion rate. That was a failure that we got. And then what happened to the erosion rate? It dropped. Okay? What we ended up seeing in that case is that the seepage almost self-healed itself. Okay? Because you got a collapse, the collapsed material laid on top of the seep, and it wouldn't let it go. Okay? Until all of that material basically liquefied and then could move. But it took a long time for that to occur. Okay? We did another experiment on the same seep, same flow conditions, everything the same, except this time when it failed, we took it out. Okay? So we were trying to act like we were a stream, like we were the flow. Okay? And what you see in this case is that we got much higher flow rates and we got higher erosion rates. Okay? So what I'm trying to suggest to you there is that there is a process, there is a self-healing process. Seepage can actually cause a collapse, but if you just have the collapses, the bank slope should be less. Okay? You shouldn't have as steep of a bank slope, and it should almost self-heal itself a little bit. But then when you get what happens when you get a storm event that comes through? Well, that's deposited materials deposited right there at the toe. The storm event comes through, it wipes all the material out, cleans it off, and then what do you have? You have a bank ready for seepage again. Okay? And so it starts the cycle over and over again. The other thing I didn't mention that we've done is that seepage forces and fluvial forces act together. Remember I showed you that jet test device where you stick it up on the bank and you do a jet? Well, it's just like digging that post hole. If you do that experiment when it's wet or when it's dry, it makes a tremendous difference. So seepage not only influences the bank causing a collapse, seepage influences the bank by changing the resistance of the bank to erode. Okay? And so we have to know what's going on with seepage in order for us to understand this. And these are some laboratory experiments that we did looking at the erodibility coefficient versus seepage. And basically this changes fast. Okay? Erodibility increases significantly with seepage. Okay? So what do you do about all this? That's fine. You say, Dr. Fox, that's fine. There's lots of mechanisms that can cause collapse, and I like to see collapses. Okay? But what can we do about it? Well, how can we stop this? And there's really a number of different ways that you can do that. And then again, it really depends. Somebody asked me yesterday, I said, it really depends on how much you want to spend. Okay? As an engineer, I think I could slow stuff down, but it really depends on how much, what is really the cost-benefit ratio for doing this. Okay? This is Goodwin Creek, which we studied for a long time. And then the landowner came back in and said, look, I think the erosion rates are increasing. I want you to come back in and rehabilitate this. So Andrew Steinman and his group did that. They pushed the slopes back. This is commonly what you would see. Okay, they went back to a 2-to-1 or 3-to-1 slope. They put some mulch down. They put in live stakings here. There's toe protection on the toe. And so this is one of the ways that we can do that. Okay? We can actually rehabilitate a bank. At that seepage project where we were doing the seepage experiments, we actually had to attempt to restabilize the bank for the landowner. We didn't really have to, but we thought it would be courteous to do that. So one of the things we did is we put in some fence postings, put in kind of a retaining wall that would allow drainage, and then we poured a lot of soil material behind this retaining wall, almost to accelerate the self-healing process. And we'll see how that works. We just put it in a couple of months ago, so we'll see how that works. If you look in general about increasing bank stability, okay, there is a couple of different ways you can do that. We talked about vegetation before. Okay, this shows vegetation on the bank surface, on the bank top. It's also important to have vegetation on your bank face. Okay, so that's one way. From what I understand, you guys have a lot of drainage in Minnesota. Okay, and I've done a little drainage work with Iowa State. We've got a USDA project. Drainage is something that helps banks. Okay, in fact, the National Sedimentation Lab in Mississippi spent several years doing a study where they put drain pipe underneath their banks. It was connected to a well, and when the water level got up high enough in the sump, the well would turn on and pump the water back into the river. Okay, and the results, from what I understand, showed that, yeah, there was increased stability. We know that if you take pore water pressure out of the bank, it helps to increase the strength of the bank. So that's one way. Another way is toe protection. And there's a number of different ways to do toe protection. You can do kind of the green, environmental friendly way, okay, which is the use of large woody debris structures or other things like that. Or you can do hard structure, toe protection. Some of you guys may have J-hooks and things like that that divert the energy off of the toe. So there's different ways to increase bank stability. But one of the things I would mention here is that not all these techniques can be applied the same way in every location. Okay? And you have to consider what processes are going on at your location to understand how to best stabilize this. Okay? The other thing we talk a lot about, and this is the last thing I'm going to talk about, the other thing we talk a lot about is riparian buffers and vegetative filter strips. Okay? And what I would say is that these are very good practices in the right places. Okay? And it's a matter of understanding why it's the right practice in the right place. And we can do that through some modeling. In other words, one size does not fit all. Okay? And one of the things is one size doesn't fit all because our objectives may be completely different. This is from USDA. So if we're looking at just stabilizing stream banks, maybe we only need a certain length of buffer. If we're looking at nutrient removal, maybe we need a different length of buffer. Okay? So based on that objective, maybe we need to think about that. The other thing is that we have to consider the processes. Okay? Filter strips basically work because they increase resistance to flow. And when you increase resistance to flow, it slows it down. Okay? You guys ever play football and you had that little cord we used to put on? That bungee cord thing? One person would take off running, the other guy would stand back there and take off running. It was supposed to increase your stride. Okay? I was 6'4" and slow. It didn't help me at all. Okay? But that's resistance. Okay? And so resistance helps to kind of slow down the flow, and it helps for water to infiltrate in that soil. When that overland flow slows down, you delay it. And when you delay it, you drop out sediment and particles from that material, and it decreases the transport capacity of that flow. Okay? And you can get deposition within that filter. Now, filter strips are deposit areas. They need to be maintained over time. Okay? You can't just put them out there and be done with them. They have to be maintained. Okay? And what I would also say is that infiltration is the key. If you try to put a filter strip in, and you put it in waterlogged conditions or where you've got problems with soil compaction, it's not going to work. Okay? That water needs to slow down. It needs to go into the soil. And so we need to be careful about where we're putting these things. I wasn't going to go into it today, but there's a lot of process-based modeling. There's a model called VSF mod, the vegetative filter strip model, which was developed by a researcher at the University of Florida. Part of his dissertation was at North Carolina State. It does flow in sediment. You can put your soil type in. You can look at all the different things. You can look at infiltration capacities. You can predict how much flow and sediment reduction you get. Okay? And we need to use these tools to design things, in my opinion, instead of just simply specifying that we need a 50-foot buffer. Okay? One size does not fit all. The other thing I would say about a buffer is concentrated flow. When you have flow that concentrates, if you're putting a buffer at the end of a concentrated flow path, and that flow path is just going to cut through the buffer concentrated, it's not going to work. Okay? Concentrated flow is the nemesis of all vegetative filter strips and all buffer strips that you can have. Okay? I can show you data on sediment and pesticide data that Bayer Crop Science compiled a couple of years ago, over 107 different studies, I think, that showed that concentrated flow was one of the most significant factors affecting performance of a vegetative filter strip or riparian buffer. Okay? One of the things we're dealing with in eastern Oklahoma, okay, Oklahoma is not flat. not all of it, okay? I'll tell you that. Okay, the eastern part of the state, we have the Ozark Mountains. They're not big mountains, they're not Colorado mountains, but they're a little bit, they're hills, okay? And one of the things we're dealing with over there is riparian buffers, but we have gravel subsoils, okay? And those gravel subsoils, in some places in our floodplains, the gravel will actually come up to the surface. In fact, when in our study areas, we can have a 2 or 3 inch rainstorm event, we can drive our cars on the floodplain 2-3 hours after it rains and not get stuck, okay? So where's that water going? The water's going down. Okay? And when the water goes down, it hits the gravel underneath and it goes right to the stream. And so we have a very active research project that's funded by the USGS, looking at the fact that if we put these riparian buffers and vegetative filter strips in, but is there a pathway underneath, and is that circumventing the effectiveness of the riparian buffer? I gave a presentation in Brussels talking about vegetative filter strips and this process. And I had people from France come up and tell me that they don't like buffers because they think this is happening, okay? So don't just go out and blindly say 50-foot buffer. You need to consider the site-specific conditions, okay? So let me conclude and wrap up. I didn't talk as long as I thought I was going to. That's good, okay? Lunch is earlier today, okay? So what I want us to tell you is that streams are dynamic systems. Okay? And it's not about what's happening at your specific stream bank. It's about what's happening within the greater system. Okay? Although activities at your spot can influence others in different places on your stream system. Okay? But these stream systems are dynamic. There's a lot of different disturbances. Okay? These disturbances can be ag, they can be urban, they can be in channel. There can be precipitation disturbances, right? That's something I didn't mention earlier. But if your climate is changing, if you're getting heavier rainstorm events over a shorter period of time, you're getting more water that runs off, that is going to change that dynamic. Okay? And I think what you guys have seen in Minnesota is the same thing that we're seeing in Oklahoma. It's the same thing we see in Mississippi. Sediment or stream bank erosion is a significant component of the total sediment yield that we have. Okay? It's a significant component. And studies have been done all over the place looking at that. What I would tell you is that the mechanisms are interrelated. You have flow, you have mass wasting, you have seepage. And so activities that you do on the landscape could potentially influence some of these mechanisms. And all that suggests, in my opinion, is that we need to consider using some of these tools that have been developed. They're very process-based, okay? They're not empirical, so they're not dependent on the condition where you're at, okay? As long as you put the information in for your bank, measured for your properties, these models will give you what's going on in terms of the fluvial erosion and the mass wasting. Okay? I have a research website. If you're interested in learning more about this information, you can go to that website. A lot of our work, and I should probably acknowledge both the NSF and the USDA. This is an old USDA emblem because that's where we got the funding from. But they've supported this work, and we're very excited about continuing on. We hope to continue collaborations with Dr. Gupta. We've already kind of talked about maybe plans for coming back this fall. Maybe we can get down in some of those banks and get a little muddy. So, thanks.
We're running a little ahead of time, so we've got plenty of time for questions. And,
Great.
I think we may even have some questions for Dr. Seeley and Mr. Kessler after Dr. Fox. Questions, right here.
I came across an old geology textbook. They talked about Minnesota since the glaciers left here only 10,000 years ago, relatively speaking. We have what this book called incomplete drainage, where nature, natural course would be to fill in the lakes, deepen the streams. Is there any validity to that, and what kind of implications would that have to what we're dealing with?
Boy, not being from Minnesota, I'd hesitate to answer that without knowing all the details to that. But again, I think it goes back to what I said earlier. You better consider the whole system and the whole process before you start doing some of that.
You had that series of slides about the stages the channel goes through.
Right.
Are those centuries long, or they depends?
It depends on the stream system. That's another one of those. Somebody told me yesterday I use the word depend a lot, and it's a good extension answer, but I think it's fine. It does depend. It depends on how long. It depends on the stream system and what disturbance it's trying to respond to in that case. We can see stage 4 channels, stage 5 channels that are fairly rapid in moving to stage 6, and in other places it's not. There's some streams that we have in Oklahoma that are right now at stage 3, and they've been at stage 3 for the last 30, 40 years. Now they got to stage 3 because we had disturbances probably from human activities potentially that ended up resulting in a stage 3, but they're fairly stable stage 3 channels. So it really kind of depends on the situation, the system.
Do you see, in your view, differences in the processes that are acting on the very high, the 200-foot bluffs versus
Right.
the 10-foot banks?
Right. So you guys in Minnesota have bigger bluffs than I've dealt with. So I will put it that way first. But I think, I think the height of that is going to control which processes potentially act on that. So for example, and one of the things that I think you saw probably a lot of in Drew's presentation was that you've got a steep bluff and then you've got a large floodplain surface that's on the other side. And so a lot of cases you can get water when it comes up, it actually spills out onto the floodplain as opposed to going, as high as a bank and spilling over the top of the bank in that case. So you have very deeply incised channels in that case. And so I think the heights, will absolutely control which processes you may need to consider. I think at times though, even when you have steep bluffs, you get failed material from the top that may fall down onto the toe, may try to protect that toe, but then if you get a stream stage that rises up, it takes that material away, allowing potentially additional failures to occur.
One right here.
Have you got any experience in geocell material?
No, I'm sorry. The question was, do we have any experience with geocell materials, like geotextile fabrics and those type of materials? We had the opportunity this year through the Oklahoma Water Resources Board to get $2 million in funding to stabilize a stream system on our campus. And one of the things that we did consider was geotextile fabrics, and I know a lot of people have used those. The problem with those fabrics is the expense. And so the expense goes way up per linear foot of bank that you're trying to rehabilitate with those fabrics. What we wanted to try to do was more of a natural using biostabilization, but that was definitely something that we've considered. I know people have used those in several different places. So.
In your area, have you noticed lateral seepage and slumping and failure on parts of the landscape away from rivers and
Right.
migrating ravines and gullies and such?
Right, yeah. I have been the question was, have you seen these type of seepage features in other parts of the landscape, gullies, ravines, those type of things? And what I would say is I haven't specifically done research on that, but my collaborator, Dr. Wilson, has specifically, his focus is not on stream banks, his focus is more on gullies. And primarily gullies that form in fields and on edge of channels. And what he's ended up finding is that there's a lot of seepage processes associated with something called piping, soil piping, which is actually a macropore that forms underneath the soil. And what they end up seeing is that these gullies will reform over and over in the same place, and there's no surface runoff process to actually cause this to form. So it's got to be by a seepage process. I'm working with a former graduate student that is now a professor in Turkey, and I think I heard about some of this yesterday on the tour. They actually have hill slopes that the Department of Transportation has built on the sides of their roadways, and they're actually seeing seepage processes out of there causing failures and having sediment get deposited on roads and things like that that they're having to come back in and clean up. So I think absolutely you're going to see these processes not only on stream banks. You're going to see. I mean, one of the biggest things with seepage and piping is not on banks, right? More seepage and piping work has been done on dams, right? So if you look at the big dam failures that have occurred, a lot of those have occurred because of seepage and piping. Okay? Those collapses are that result. So I think these things are going to occur really across the landscape. One of the things that we are kind of starting to talk about a little bit in Oklahoma is in Oklahoma we're starting to go to a lot of no-till. And what's happening is no-till does a great job at preventing runoff, but it puts more moisture in the ground, and that moisture in the ground's got to go somewhere, and it's going to the stream. Okay? And so we've started talking about no-till. We don't have any data to support kind of the hypothesis, but that's something that we've started to talk about.
One here.
You didn't mention watershed stability,
Mhm.
taking watershed approaches to reducing stream flows or
Right.
at least stabilizing stream flows
Mm-hmm.
to reduce stream bank erosion.
Right, right. So there's a number of different things that you can do within the watershed to look at, and again, it's all goes back to that whole system approach. We have classic conditions where we have an urban area on the upstream part of the watershed, and that urban area in the upstream part of the watershed is growing at such a rapid rate that it's putting more water into the stream and causing those banks basically to collapse. And so there's a lot of different approaches from an urban standpoint that you can use to actually try to capture and delay some of that water, right? We've used a lot of storage, water detention structures that we've used commonly throughout the past. There's a lot of work going on right now, especially in my department, with bioretention cells, or what are sometimes called rain gardens. And that's a movement of water trying to slow it down. It's eventually going to release it back to the stream, but it tries to slow it down. So I think you do have to look at it from a watershed scale approach. There's something that's causing that disturbance within the stream system. It's something that's going on within that watershed. And there's a number of different possibilities of what could be causing that disturbance.
From your experience, what part of the hydrograph is generating the most amount of erosion? Is it those peak flows, is it sustained flows?
It's usually a lot of and this is based on just the studies that I've done, but it's usually based on more of those peak flow events that we've got. It's not necessarily the base flow type events that transport a lot of the sediment. We see a lot of sediment in coming into our streams when we get collapses, okay? And one of the things that's been studied, I know Andrew Simon's done some work, I'm trying to recall, from Lake Tahoe, where they actually used B-stem and they modeled what was going on in Tahoe. And then they would come back in, they looked at reductions, and then they put toe protection in and looked at the reductions. And just by protecting that toe to keep that material from collapsing, they ended up saving a lot of that sediment that was coming into their stream system.
In Drew Kessler's presentation, you saw some slides of massive bank erosion. I suspect you probably saw those on your
Yes.
tour yesterday. Would you have any suggestions on what could be done with those? Are those hopeless, or?
Those are tough. That's tough. I don't have any specific solutions right now. What I would say is that those bluffs are so high and the slopes are so steep that what the channel is trying to do is it's trying to widen. Okay, and the question is that something that we want to try to slow down? Or is it something that we just consider to be a natural process? Some of the mechanisms, I think Dr. Gupta is going to talk about this, and he's done some work on this on those banks. But the mechanisms there are heavily related to the soil water content within those bluffs. And so if we're going to try to slow it down, we have to start attacking the mechanisms that are acting on it. And that could be additional drainage type material that could be placed into the bank. I don't know if Dr. Gupta's come up with his solution specific to this area, but those are some of the considerations that we've considered looking at. We actually, on the Cow Creek project, the one that's going through our campus, we actually have designed a new bank facility research center. And what we're going to have is we have a meander bend, and we have it divided up into 6 different reaches, and we actually have drain pipe installed underneath there, and we're going to control the pore water pressure, and we're going to see if we can control it enough to actually make a difference in the amount of erosion we get around that meander bend. So I think it all goes back to understanding the processes and then trying to attack that process. On a small scale, we tried to stabilize that little seep spot that we found there in Mississippi. You're going to need some big scale stuff for the bluffs that are here. So.
Any other questions? Dr. Fox, thank you so much.
Appreciate it.